Now I have 28 to 33 days to replace these vessels. We had to align the vessel movement and crane placement with other projects. That's right. I've got congested facilities. I've got big vessels. I've got little time. And now I have competition. I have a turnaround and maintenance going on in the same facility, the same shutdown, as well as 2 other capital projects. One upgrading the instrumentation system, one upgrading the electrical system. All competing for the same real estate. So, we thought, how do we address these challenges? So, we considered a traditional approach to constructability. We get out the as-built drawings, we get a construction superintendent, we walk the job site, we take a look. Yeah, it's about 10 meters, maybe I have 3 meters here, it should be okay. We didn't feel that would do what we needed to do with the constraints we talked about. So we felt the solution was to do 4D modeling. So what is 4D modeling? 4D modeling is 3D modeling plus clash detection all over time. Now, what makes our application of 4D modeling a little bit unique is the addition of 3D scanning. So, let's talk about each one of these things individually. 3D scanning. 3D scanning is the process of analyzing a real-world object or environment to collect data on its shape and possibly its appearance. The collected data can then be used to construct digital 3D models. So what we did is we took these devices at certain places throughout the facility and we captured a 360-degree view of the existing facility. The product that we received from there is called a cloud point. And this is the product from the 3D scanning. You see, it's quite detailed. Every valve, every switch, every pipe, every control panel is identified through this 3D scanning. The next element was 3D modeling. I think most of us are familiar with 3D modeling. It's been around for a long time. This is where we can take a computer-generated graphic of an object in its 3 dimensions. We applied 3D modeling to our challenges by modeling the vessel. These were emplacement-in-kind vessels, so we knew the size and shape of the vessel. We modeled the crane. We had done some pre-constructability work to analyze the size and type of crane we would need for the project, and then we mounted it in the computer. Finally, the self-propelled mobile trailers. These are standard items, so the dimensions, sizes we get from the catalogs. So we modeled these 3 items and embed them into our cloud point. Clash detection. 2 objects cannot occupy the same space at the same time. A clash occurs when elements of different models occupy the same space. Clash detection helps in effective identification, inspection, and reporting of interfaces. So, this is one of my favorite clashes. You can see we have a utility pipe going right through a structure. We use clash detection into our projects in 2 different ways. We have what we call soft clashes and hard clashes. A soft clash is when an object is close to another object. So in the software, we can put a radius around our solid object, and anything that comes within that radius is a close tolerance or a soft clash. If the models touch the vessels, then we have a hard clash, and we'll show you a little more of that later on. And then finally, we take these 3 elements and we all put them over time. So, what does this look like? So, we put the 3 elements together and we develop this model. As you can see here, in orange is our vessel. All the area in gray is the actual site as it exists. Doing the 4D modeling, we can now see before the shutdown, we'll assemble our crane. After the 5 days of de-inventory, we can start our vessel movement. So we bring in our self-propelled mobile trailers, we perform the lift, we rotate, we put on the trailers, and then we can move it through the actual site, and then finally out. Since it's a model, we have the ability to zoom in, pan out, rotate. So if we want to take the detail of the lift, you can see here, here's the vessel that we modeled into the actual facility. Assemble the crane, bring in the trailers, perform the lift, rotate on the trailers, and then out of the facility. So that's all great. Some nice pictures. But what did we learn from all that? Well, the clashes. This is what's important to us. We have two types of clashes. Clashes in yellow are the close clashes, when we talk about we're close to something. The clashes in the pink are the hard clashes, where we're going to have an interface with something existing within the facility. So let's take a look at some of these clashes up close. So here we see, when we put down the pad that the crane will sit on, we see now that there are several pipe stanchions in the pipe rack that are going to interfere with the plan. Everything in pink is a hard clash. Instrument panels, existing equipment. This is one of my favorite clashes here. Here you can see, as we raise the boom and we rotate, our counterweights are going to take out a light bulb. So do this 4D modeling, we actually have eyes in the back of our head. Another one of our hard clashes is bollards. Bollards are put in place to protect equipment. So there's many of the sites, as you can see through here, we had many bollards that we identified that we had to address before we started the movement of the vessel. Then there are the soft clashes. By putting a radius around the vessel as we move it through the facility, we can now see where we're going to be close to something. So here you can see we have about 2.5 meter clearance between fire hydrants. We have a close clearance between the light poles, close clearance around the stairs. And with this information, we can make a decision. Do we feel confident that we'll be able to move this vessel through and not interface with these things? Or do we be proactive and remove these things from the facility prior to the shutdown? Overhead lines. We can, through the scanning, we can pick up small details such as overhead lines. We can know the dimensions from the vessel. And if anyone's ever tried to move a vessel underneath power lines here in the kingdom, knows there's a lot of rules and regulations around that. So the old vessel's been removed. Let's bring in the new vessel. And then the detail of the lift, swing, and place. And you can see here just how tight this is. We're going to put this big vessel right in between two existing vessels. So what was the value gained from all this exercise? Well, first, confirmation enhancement of the project schedule. By identifying the hard and soft clashes before we go to the site, we can now identify what work has to be done ahead of the shutdown in order to facilitate no delays during the shutdown. Shutdown schedule and activities. Again, we have a better understanding of the scope of our work prior to entering the facility. Installation of dress vessel. This is interesting. Dress vessel. A dress vessel is a vessel that has the platforms and ladders installed. Our original plan for this project was to bring in the vessel and install the ladders and platforms during the shutdown. By modeling the vessel with the platforms and ladders, moving it through the facility, doing our clash detection, we found out that we can assemble the platforms and ladders pre-shutdown. hence saving us time during the shutdown to do that assembly work. Confirmation enhancement of project constructability. We talked about the constructed area, so we showed how we can move through these tight spaces. Knowing our scope, we can reduce on change orders, right? We have an understanding of all the work that's required, the work required pre-shutdown and the work required during shutdown. Plan on necessary ramp-up procedures, right? We talked about the overhead lines, right? Knowing about my overhead lines, I can get my approvals done ahead of time and not have to face that issue during the shutdown. Approval of the lift plans. By having this graphical representation of the work that we're going to do, it's easier to communicate to the other stakeholders, particularly our loss prevention people who scrutinize our lift plans, to show that what we're doing is very safe and executable. Communication to project bidders, end users, and stakeholders. Our foremen and our superintendents, we had to get their buy-in on this plan. And again, the graphical representation helps communicate what we're going to do. The other two projects, we needed to communicate to them. Where's our vessel going to be? When is it going to be there? How long is it going to be there? So they can plan their work as well. Communicating to our inspection team. Communication to the bidding, to the contractors. We included this in our bid package. So the contractor can now get a better idea of his scope and give us a better pricing. Verification of existing nozzle size and orientation to vessel fabricators. This was an unintended benefit. The plan, because we had such a short shutdown, was to take the pipe spools, unbolt them, put them on the side, replace the vessel, and then bolt the pipe spools back up. In order for that to happen, the nozzle projections and orientations had to be identical to the existing vessels. By reviewing the 3D scan, we could dimensionalize the nozzles and ensure the fabricator had them in the exact same spots. Cost. Everybody will ask me, Mike, what does this cost? Constructability simulation costs were about 0.25% of the total project cost. This project was about $100 million, so we're about $250,000. The risk, 1 day of plant shutdown, could be $12 million. So you can see the risk reward there is pretty clear. 4D was first brought up in 1998 in a paper by John Egan, and he said redesign should take place on the computer, not on the construction site. So we showed you our big plans and our nice animations and our clashes, but what did it really look like at the end of the day? Pretty close, right? And of course, no vessel replacement is complete without a cake with a vessel on top of it. So I'm happy to say to date that 10 of the 16 vessels have been replaced. And I'm also very happy to say that each of these replacements has completed its project 7 to 5 days ahead of the planned schedule. It saves about 25% of the time during the shutdown. Now, I'd like to take the credit for the 4D modeling for that, but I'm sure there's a lot of other factors, but I'm sure the 4D had something to do with it. Thank you very much.
Thank you, Mr. presentation. I would like now to please call Engineer Mohammed Abilal to recognize our speaker.
Thank you for having me, really. Thank you.